Welcome to our podcast, Keep You Flying. In this podcast, Lufthansa Technik's experts deep dive into their field of knowledge in aircraft MRO and provide exclusive insights into the design and production of parts for VIP, special mission, and commercial aircraft.
This is the fourth and last part of Dr. Henrik Schmutzler's series. In the first 3 episodes, the expert for composite manufacturing at Lufthansa Technik talked about the various benefits that the new robotic system brings for repairs on airframe related components made out of composite materials. Since most structures are hybrids of 2 or even more materials, this final episode is to show how the capabilities of the robot provide even more flexibility and versatility with respect to the usually far broader material and component mix generally found in airframe-related components. While for years we were conducting research on all different kinds of materials and procedures, our overall goal was to handle most or even all of them on the same platform in terms of robotic deployment. This now also includes the replacement of metal parts, for which our robot provides a good number of benefits. Metals such as aluminum and titanium are usually the materials of choice for those rather highly exposed airframe-related components that, due to their position on the engine, are much more prone to foreign object damage. The aluminum lip skin of an engine's inlet cowl, for example, is part of the aerodynamic structure of the air intake. Besides being prone to corrosion, it is also heavily exposed to impact damage from bird strikes, hail and runway debris, or even ramp vehicles. The result is often extensively bent metal that usually mandates a replacement of the entire lip skin segment. The latter, however, consists of an immensely complex curvature in several dimensions, which is fixed to the inlet cowl structure with hundreds of rivets around the entire surface. This complex geometry, as well as a large number of fasteners, made the conventional and manual replacement process for these components extremely time-consuming. As new lip segments from the original equipment manufacturers only come delivered in oversized contour dimensions and without any mounting holes, both the final contour dimensions as well as the positions of all mounting holes have to be precisely transferred from the original to the replacement part, until today an entirely manual and highly iterative process. On top of that, there are a number of variations between all different inlet cowl types we handle, from splice positions and rivet patterns to material mixes. Every year, my colleagues in the Hamburg workshops for aircraft-related components manually replace a double-digit number of lip skins, with each replacement taking several shifts on average. The underlying manual process encompasses the following steps. First, removal of fasteners from lip skin. This alone can be exhausting on joints over time. Second, transfer of holes and outer contour to a template. Third, performing an iterative process to fit the replacement part into the inlet cowl. Fourth, transfer of holes back to the replacement structure. Fifth, deburring, countersinking, and final fitting of the replacement structure. For my colleagues on the shop floor, especially the dull and repetitive tasks, such as removing hundreds of steel rivets, could be exhausting over time. Being that the cost for a replacement part is very high, all steps have to be taken with the utmost care, which in turn demands a lot of time. In addition, steps 3 and 4 have to be repeated several times during the manual process. Hence, with the robot already in service for other aircraft-related components, our aim was to also automate parts of the manual process, in order to not only relieve our colleagues from the aforementioned exhausting tasks, but also to attain vastly reduced turnaround times by removing the iteration steps. To achieve such high precision levels, our robot now relies on the following partly automated process steps, whose feasibility we successfully demonstrated on numerous test parts during the development phase. First step, scanning of the entire inlet cowl. To clearly identify and record the position of all rivets that fasten the damaged lip skin to the inlet cowl as well as the outer contour, we use the same scanning equipment I already described for the composite repair processes in episode 2 and 3 of my series. The combination of geometric data and real images enables our structured light scanner to clearly identify all relevant features. Its measurements are then recorded into a three-dimensional digital twin, in which the human supervisor can make final adjustments on screen before starting the next process steps. Second step, drilling out all rivets fastening the damaged part. Based on the positions recorded during the scan, the robot switches to the drilling tool and drills out only those rivets that fasten the damaged lip skin segments. Once the drilling procedure is complete, the loosened lip skin segments are removed manually. Third step, transfer of pre-recorded geometry. Once the original part is removed, my colleagues bring the replacement lip skin to the robotic chamber and place it on special 3D printed tooling that was designed in our in-house additive manufacturing center. The 3D printed tool is necessary to allow the required process tolerances to be transferred to the complex-shaped replacement part. The robot then automatically exchanges the milling and drilling tool for a scriber, with which it transfers the outer contour's pre-recorded geometry to the replacement part, clearly marking the positions for the subsequent trimming of the latter to perfectly fit the gap. Fourth step, manual trimming of the outer contour. As no more iteration is required due to the precisely transferred geometry, colleagues can machine the final contour in one step, saving a great amount of processing time. Fifth step, automated drilling of the fastener holes. Once the trimmed replacement part is manually placed and punctually fixed into the gap, the robot switches to a pre-selected drilling tool and drills out the several hundred rivet holes at exactly the positions it has derived from the digital twin. This process also includes the subsequent deburring, reaming, and countersinking of the drilling holes. Sixth step, manual fastening with rivets. The final riveting process is done manually. Based on the successful demonstration of these capabilities, we could prove that the partly automated robotic process significantly improves the efficiency of the lip skin replacement process to a great extent, while at the same time taking all manufacturing tolerances and potential service deformations into account. Especially the digitization and transfer of the relevant geometries from the original to the replacement part reduced the overall lip skin replacement time by several hours. In this case, the reduction of working hours is an extremely welcome benefit for the affected mechanics, as they are happy to be relieved from the rather strenuous duties of iteratively flip-flopping from the original to the replacement part. Moreover, they can perform the trimming process at speeds that would not be possible in the manual process without risking the costly replacement part. The results from the demonstration phase are so promising that we aim to have the robotic lip skin replacement process certified for the first inlet cowl types with a subsequent introduction to series production in our Hamburg Airframe Related Component workshop. The final capability range is planned to encompass the 5A, B, C, and 7B subtypes of the CFM56, as well as the IAE V2500. Although from my perspective, there are many more interesting stories to tell about our new robotic system, I hope my series at least provided you with a good overview of what benefits robotic technology can bring to the MRO of airframe-related components. I would like to thank all contributors here at Lufthansa Technik, as well as at ISAM, and all my readers on LinkedIn for their positive feedback, reactions, and comments. Any feedback is highly appreciated.
Thanks for joining this episode of Lufthansa Technik's podcast, Keep You Flying. If you'd like to hear more from us, don't forget to subscribe. For more deep dives, also check out our LinkedIn channel, where we regularly share expert content.